Hello everyone. So today we're going to start on 11.2, which talk about what would happen if we have a complex solution to a differential equation. So the general idea is the following. So consider that from last section, let's say we're given a second order constant coefficient differential equation, linear constant coefficient differential equation in the form of let's say y double prime plus by prime plus cy equal to 0. So notice that we're still only focusing on homogeneous equation. And yes, later in section we'll talk about what happens if they're non-homogeneous. But we just simply focus on homogeneous for now. Notice that this equation, this differential equation, has a quadratic characteristic equation. Quadratic characteristic equation, and which looks something like this, which is r squared plus br plus c equal to 0. And based on the fundamental theorem of algebra, this quadratic characteristic equation, oh, I forgot the word equation, must have two roots. And the problem is, so this characteristic equation, it must have two roots. And these two roots could be real or imaginary. So the problem here is the following. If they're imaginary, it doesn't change the way the solution look like. So imagine, so it must have two roots, and let's say those two roots are R1 and R2. Then the solution set to this equation will be in the form of since we have the unknown function y, and I'm going to assume the independent variable is x, so then would be y equal to c1e to r1x plus c2e to r2x. So whether it's real or imaginary, this is still what the solution set look like. The only problem here is the following. If R1 and R2 are complex roots. And yes, because if they're complex root, they have to be two distinct roots. So if R1 plus and R2 are complex roots, then we need to define ye raised to a complex numbers. A complex power. Raised it to a complex power. And when we do that, we define what we call complex exponential function. So complex exponential functions. And that's what happens when you try to raise e to a complex power. So what is the complex exponential function? So well, let's try to define it. So definition. So obviously we all know how to raise e to a real power already. So the only part that we really want to define is what happened in the imaginary part. So here's what it is. So the complex exponential function defined just for the pure imaginary part is given by this definition. Defined for the pure imaginary part. So meaning no real part, just the imaginary part. And then of course we'll put them together to form the complex exponential function. But if you just have the imaginary exponent, for the pure imaginary numbers, let's say ix with x being real. So that's how we define an imaginary number, is to multiply the imaginary part with a real number as the coefficient for I, is given by the formula right here. Oops. E to the ix is equal to cosine x plus I sine x. And you probably remember Mr. Bernhard gave you this formula. Okay, the CIS function, CIS function. Okay. So it's so the reason why this is the definition of e to ix is because of the Macron series for e to the x, cosine x, and sine x. So show you a little proof. Okay, so proof is basically come from the definition or the Macron series for e to the x. So you probably remember that from BC calculus. E to x has a power series that represent e to x as by the function 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial, and so on and so forth. So that's what the infinite power series for e to the x look like. Now, if I now plug in e to the ix, then what happened is they would basically change the equation to 1 plus ix squared over 2 factorial plus ix to the third over 3 factorial plus ix to the fourth over 4 factorial plus ix to the fifth power over 5 factorial, and on. And now when you think about raising I to power, notice that it follows a very simple cycle of 4. So they repeat the same 4 value over and over again. So therefore I say that e to ix will equal to 1 plus ix plus this become I squared, which is negative 1. So technically become minus x squared over 2 factorial. And I to the third become negative I x to the third over 3 factorial. And I to the fourth become 1 again. So therefore just become x to the fourth over 4 factorial. And then I to the fifth become just I. So become plus I x to the fifth over 5 factorial. And this pattern continue on. And now if you look at this, notice that now half of the terms are real, and the other half of the terms have the I in it, which become imaginary. So therefore I can now group them separately into the following. So therefore, you know what? I'm going to take this off because I don't want to keep writing them. I'm going to collect all the terms that are real together. So it become 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus ... And then for the term that have I will pull out the I. And that would leave me with x minus x to the third over 3 factorial plus x to the 5 over 5 factorial minus ... So notice that I actually split this single infinite series into 2 infinite series. And one contain only even exponents with even factorial on the bottom and alternating sign. One of them have only odd power exponents with odd factorial on the bottom and also alternating sign. And hopefully some of you might recognize that this first series right here is actually the cosine x series, while this infinite series, while the second infinite series is the sine x infinite series. So therefore arrive in this expression. Oops, I do need this one. Okay, and therefore arrive in this expression, which is cosine x plus I sine x. And that arrive at our definition. Now, with that definition being defined, now I can define what is a complex exponential function. So now I can define the following. The complex exponential function defined for a complex number, let's say a plus bi, is given by this formula. So if I have e to the a plus bi as a complex number, then realize that when you add the exponent together, you are basically multiply two terms that have the same base. So therefore, that becomes e to the a times e to the bi. And e to the bi now can be defined using the definition that we just defined. And so therefore become e to the a multiplied by cosine b plus I sine b. And if you recall, learning from Mr. Bernhardt, and this is kind of the magnitude, and then the b is like kind of the angle rotation. Now, if I want to define a exponential function that has x in it and have a plus bi as the coefficient, then I will have this. And this, same way, it would equal to e to ax e to the bix. Oops, I did it again. E to the bix. And so e to ax will stay, and then this become cosine bx plus I sine bx. So this one will be e raised to a complex number, while this one become the complex exponential function, where you have a real value that you plug in for x, but it has a complex coefficient in front. Okay? So in this second expression right here, e to a plus bix, we do kind of assume x have to be a real number. It's just that it has a complex coefficient in front. And of course, if x is not a real number, then it probably just combine, when you plug in x as a non-real number, it would just basically combine into a different complex number, and then it can then still be defined by this formula. All right. Now, the interesting thing about it is the following. When we define our complex exponential function using this definition, it actually have a lot of advantage that we can make use of. So let's talk about different properties that are important or about this definition. Okay, properties for complex exponential function. So defining e to ix equal to cosine x plus sine I sine x has a lot of advantages that we want to explore. Defining e to ix equal to cosine x plus I sine x has a lot of advantages. And some of these are extremely important in what we need to do. So I want to show you what they are. So number one is the length of the complex number. So you probably remember learning it back in Algebra 2. Let's say when you're given a complex number, let's say a plus bi, we define the quote-unquote absolute value, but technically speaking, this is a length function. The absolute value of a plus bi is given by the formula square root of a squared plus b squared. Notice that you don't do bi squared. You just take the coefficient and then take the square root of the sum of the square. Because in here, once again, we're actually defining a plus bi as a vector ab on the complex plane. And therefore a squared plus b squared, a squared plus b squared equal to the magnitude of that. So if you recall, this is, let's say, our complex plane where we have a and bi. And so therefore, if you want to define a imaginary number, let's say right here, then this imaginary number would be defined by this thing, a plus bi, but it refers to the coordinate ab on the complex plane. And so the length of a plus bi become the length of this vector, which is basically the length of the vector ab. So which is the reason why you actually don't put the I in the formula when you do this. Now, what would be the advantage of defining e to ix using this concept? Is because e to ix actually form what we call unit vector. Why? Well, because the following. E to ix, if I take the length of that, that's the length of cosine x plus I sine x. And according to the formula that way on the top, that means that's square root of cosine x squared plus sine x squared. And that would just be square root of sine square x plus cosine square x. And that, based on Pythagorean theorem, become 1. So therefore, would be square root of 1, which is 1. So it's actually pretty nice in the sense that when you have the define the complex exponential function this way, the cosine x plus I sine x part actually have a magnitude of 1, and therefore when I define it using a complex number, so if you go back up to the top, then that will allow me to define that e to ax become the magnitude, while cosine bx plus I sine bx would always generate a length of 1 and therefore does not affect the magnitude of the complex number. So that's a very nice property to have. Number 2. One of the important things about about exponential function is that it has several established properties that we know. So for real numbers, let's say n and m, we know that when I take e to the n multiplied by e to m, that just becomes e to n plus m. And that's what we learn, that's what you probably remember learning in algebra, I would say probably even in algebra 1, when we first learned about exponents. Okay, that you remember and you learn that when you multiply two expressions with the same base, you add the exponent together. But of course, at that time, you only know how to define real exponent. But now we can now define complex exponent. The question is, does that still follow the same rule? And of course, if you know, math is an internally consistent system. So therefore, when we introduce something new, we want to keep it consistent with things that we already established. So in this case, we hope that when we define this same property using complex number for n and m, it will still work. So let's see if that's the case. So suppose I do e to the ix multiplied by e to the iy. we're hoping that will equal to e to ix plus iy. So let's see if that's the case. So if I do that, that would mean that I would say this is basically cosine x plus I sine x multiplied by, so define e to iy the same way, so become cosine y plus I sine y. So look like we just have the FOIL. So I'm going to FOIL. So therefore we will have cosine x cosine y plus I sine x cosine y plus I cosine x sine y, and then plus I square sine x sine y. So notice that I square actually make it into a real number. So I square actually cancel out and become -1. And therefore, if I now look at this, I notice that I have two real terms, two imaginary terms. So I'm going to group them together. The real term would be cosine x cosine y minus sine x sine y. Oops. Plus, and I'm going to pull out the I from this here, and then what I have would be sine x cosine y plus cosine x sine y. And now here comes the important part. Both of these are actually trig identity. Cosine x cosine y minus sine x sine y is actually the identity cosine x plus y. And and then sine x cosine y plus cosine x sine y is also a trig identity. That would be sine of x plus y. So therefore, after all this combining and simplifying and using trig identity, it comes out to be cosine x plus y plus I sine x plus y, which, if you think about it, is the same as e to the x plus y I. And therefore showing that e to ix times e to iy actually equal to x plus iy, or xi plus yi, of course. So that's actually pretty, actually maybe I should write it this way. I should write it as ix plus y, because I put the I in front. So that's actually pretty neat, because it showed that the multiplication between two complex exponential function would actually work out exactly the same thing as if it would with real exponent, is that they would actually add together, which is extremely important and very helpful, because that would mean that we don't have to learn new math just simply because we're now plugging in complex number. And you can also imagine the following. Okay. E to the negative ix is 1 over e to ix. And so therefore, e to the ix over e to iy would equal to e to the x minus y, or I times x minus y. So both of these are also true. Now, of course, you probably remember that your math teacher in Algebra 2 told you, we can't have the complex number at the bottom. And that's true. And we'll figure that out, how to deal with that later on. And when we actually do evaluate them, and then we'll figure out how to deal with the e to ix in the denominator. But for now, we can still define negative exponent with complex number and division between two complex exponential function the same way we would with real exponent function, real exponential function. So which is extremely important. Now these two are definitely important, but not as important in what I'm going to show you next. So what's the next important properties? I guess number 3. That we need to know about complex exponential function is the following. It's their derivatives as well as their integral. Okay? So let's talk about these two things. Now, why are these two things important? Well, because the idea here is that we want to use complex exponential function to represent solution to a differential equation that have complex roots, for the complex characteristic roots. And if somehow the derivative and integration of a complex exponential function is not the same as regular exponential function or real exponential function, then it probably going to affect the way we use them in solving differential equation. So that's definitely mean it's no. I mean, it's just completely ruin what we want to use it for. So what we want is that even though it's a complex exponential function, it still follow the same exact differentiation and integration rule, just like the real exponential function. So here we're hoping is the following, is that we're hoping that the differentiation rule, and I'm going to try to prove it to you, is that the differentiation and integration rule for e to ix is actually the same as e to the x. So how does that work? So show you. Let's say I want to take the derivative of e to ix. Let's say differentiate d over dx of e to the ix. Now, obviously, we don't know the rule for this, so I can't really do that. But I do know what e to ix is. E to ix is the same as cosine x plus I sine x, with I being the imaginary component that is a constant, technically speaking. So if I think about it, then I know how to differentiate cosine x, so that just equal to negative sine x. Okay, and what is I sine x, the derivative of that? That becomes plus I cosine x. Now, at first that doesn't look like what we know, because remember, what we know is that we have the cosine x represent the real part and the sine x represent the imaginary part. Now, this actually kind of flip-flop the two. So what do we do with this? Well, interesting thing is this actually represents something that we can factor out. Now, you might not see what we can factor out, but I'm going to help you out by writing the following. See the negative in front of the sine x? That technically is I squared. And now you can see that I can factor out an I from both of them. And when I do that, I get cosine x plus I sine x. Voila! That means this equal to I e to the ix. That is what d over dx of e to ix equal to. And that followed the differentiation rule that we know. And the differentiation rule that we know is this one. D over dx of e to the ax is the same as a e to the ax. So that rule, if you remember, probably learning from me in BC Calculus, allow you to differentiate e to a coefficient in front of x. And that simply move the coefficient in front of the entire function. And so here, the coefficient is I, and therefore that I get moved to the front. And because of that, it follows the following. And would be the integration rule. If I want to integrate e to the ix dx, the integral of that would actually equal to 1 over I e to the ix plus c. And yes, you can actually rationalize this. And if you do rationalize it, you basically multiply I over I into the front of this thing. And that would just make it equal to negative I e to ix plus c. So that is the integration rules. Okay, however, I do recommend memorize just this part right here, the front part, because it mirror an integration rule that you probably already know. Integral of e to ax dx is equal to 1 over a e to ax plus c. So that's for real coefficient in front of the x. And as I say, it turned out to be the same for e to the ix. So now come the next question is, okay, so the imaginary things worked out. So now what happens if you have a complex root? How does that work? So, well, let's find out. So let's say what happened to the following. So let's see, this is what, 3? So I guess I'll number this one 4, why not? Okay, so 4. What if now we have a complex root? So let's look at it this way. What if we have e to the a plus bi x? And let's say I want to take the derivative. So now remember, this is just e to the a times e to the bix, e to ax times e to bix. And so therefore just e to the ax multiplied by cosine bx plus I sine bx. Good. So therefore, if I want to form the derivative of this thing, I will just do the same thing I did before. And we'll take the derivative of e to the a plus bix. That means I'm taking the derivative of, and yes, I know the video is already past 30 minutes, but I'm just want to finish up this part, and then that will be it for today's video. That will mean d over dx of e to the ax cosine bx plus I. Oh, actually, you know what? Maybe I'll do it this way. I'll just say e to the bix. And what I'm going to do is I'm going to take the derivative of both of these things. Together, since the product, I'm going to have to use product rule. So product will dictate that will be e to ax d over dx of e to bix plus e to bix d over dx of e to the ax. So notice where I have formula for both of these, which is right up here. Right here and right here. So both of them actually satisfy the same exact formula by putting the coefficient in front of it. So therefore, if I continue, that just becomes e to the ax, bi e to the bix, plus e to the bix. Actually, I don't need the parenthesis here. Multiplied by a e to the ax. And now if I look at this, I can now combine them into this. So it will be bi e to a plus bix plus a e to the a plus bix. And so that, if I now pull out the a e to a plus bix together, that just form a plus bi e to the a plus bix. So that formed the derivative of e to the a plus bix. And once again, it followed the same formula that we established. And so the last thing I want to write down is this. What happened if you integrate e to the a plus bix? Well, it's followed the same exact rule. That becomes 1 over a plus bi. E to the a plus bix plus some constant c. And of course, in this case, the constant c could be complex also. All right, unfortunately, that's all the time I got. So I apologize that this video is a little long, but I do want to kind of finish all these theorems. And we'll continue some more on next video. All right, talk to you guys later. Bye-bye.